having discussed local linearity, we want to kind of revisit that idea and discuss more why we actually care about local linearity. And so the other part of this module is to talk about rates of change. And so we're going to get there, but first we need to remember the different properties from lines. So lines again are really well studied, but they also tell us a direct relationship between two quantities. And not only a direct relationship, but that relationship is also fairly nice. So we get a relationship, and it tells us how the quantities are changing over time, or how the two quantities change, or one quantity changes based on the change of one other one. And so if we remember, from module, I think 1A or even module 0, we discussed the average rate of change, and we use delta notation. So delta, change in y, are dependent variable over the change in x, our independent variable. For 2 points, again, we could also represent it like this. And so lines, we can get an average rate of change, and we said back in module 1A that we can actually use the average rate of change to approximate what we're going to call the instantaneous rate of change. And we're actually, in this module, we're going to discuss how to actually compute the average, or the instantaneous rate of change, or at least estimate it, get really close to it. Okay, and also one other connection that we made back in module 1A and in module 0 is that the average rate of change is the slope of the secant line between these 2 points. Okay, so we can think of it both algebraically and graphically. Okay, and I believe in module 0 we also discussed how to interpret the average rate of change. So for a 1 unit increase in x, y changes by whatever this value equates to. Okay, and so now we want to ask what happens to the average rate of change as delta x gets smaller. So if we decrease this value, what happens to delta y? So in essence, we're saying the limit, what is the limit as x goes to 0? And again, I have another GeoGebra demonstration here. So I have a curve here, and you can see the function over here. And I have 2 points labeled on it, P and Q. Alright, P is at the point 1, negative 1, 8, and Q is currently at 4, 28. Okay, so delta x right now is 5. Okay, and you can see I have this slider over here, and as I change the value, in a minute here, nope, and as I slide this, Q changes, and so that in turn changes my distance between P and Q. Okay, so what I really want to explore is what happens to the average rate of change. Again, this is the line in red is the secant line. So what happens to the slope? And remember, the slope is this coefficient of x here. So what happens to the average rate of change, the slope of the secant line, as I decrease the delta x, as I take a from being relatively large to something relatively small. Okay, so let's go ahead and explore that. And I'm going to zoom in here just for a little bit so we can maybe get a better view of all this. Alright, so I'm going to go ahead and start to move Q. So I'm going to decrease Q, okay, and so I kind of want to get past this hump here. And so Q is currently sitting at negative 1.2, or at a positive 1.2, and so that's delta x of 2.2. And so I'm going to continue to decrease this. Okay, so as I go here, you can see, look, pay attention to my my slope of my secant line. Okay, so I'm going to continue to decrease this, and it's getting smaller, negative 7, negative 7.04, negative 6, and now actually when I go to 0 it's undefined. But as I get really close, let me see if I can get it at 0.1 here, you can see it's negative 6.29, and all the way up here it was negative 8, negative 7, da 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 da. it appears as though it keeps decreasing, and we could estimate it to be -6. And now to confirm this, I would want to go into Excel and actually make a table of values. But I will go ahead and tell you that if you go ahead and do that in Excel, you do get it approaching -6. Okay. Now I want to go to the place where A is 0. Okay, so essentially you can see it here. P and Q are essentially on top of one another. Okay, so I've taken and decreased the delta almost all the way, well, to 0 in essence. But I want to think of this as getting really, really tiny and getting really, really close. So actually, when I do that, my 2 points form a line, and I think this will work. And this line hits the curve at precisely 1 point. And again, due to this function, and it's a special case of this but it'll intersect down here again. But the main idea is that this line intersects the function at exactly 1 point. And when it does that, this line that we create is called a tangent line. So in essence, when we go from a secant line, I have to get rid of my transparency here. So before, I had a secant line here, and when I decrease delta x to 0, I actually form what we have come to call a tangent line, where it intersects or touches the curve at precisely 1 point. All right. So let's go back into our notes and advance. So let's see. So again, what we were saying is that if we decrease the delta x to 0 in our average rate of change, we actually get what we have come to call the instantaneous rate of change, or the slope of the curve at the point A, or at the x value A. So f prime of A, remember from module 1, we said f prime was the instantaneous rate of change. We used it to approximate the average rate of change, but now that we have limit notation, we can actually have direct equality. Okay, and then as we mentioned before, we said that, well, the average rate of change, that was the same as the slope of the secant line. And through the process that we showed in GeoGebra, the instantaneous rate of change actually was the slope of the tangent line. So, and then again, I gave the definition of the tangent line. Okay, and so one way we can represent that equation of the tangent line is right here. So we said y is equal to, and this is just point slope form modified, the slope, which, since we have the instantaneous rate of change at a given point, we might as well use it instead of the average rate of change. Instantaneous rate of change is at a specific point. Average rate of change is over an interval. Okay, and then just finishing out the point slope form, we have the point that corresponds, or the point that has the corresponding slope here, so we can just form our equation of a line like so. Alright, so the key idea is we have the algebraic interpretation, we have the graphical interpretation, and we should be able to go back and forth between the two. Alright, so let's go through and do some examples fairly quickly. Okay, so example 1, I have this function which models the position of a particle at time t. I want to determine the average velocity. Okay, so I'm going to leave much of the computation up to you, but I do want to recall that, well, average velocity is really the change in, this is the change in position over the change in time, okay, from physics. And so I can represent this as s of t2 minus s of t1. And this just means the position it is at time 2 and minus the position that it is at time 1 over the difference in the two times. Okay, so go ahead and doing that here. I'll leave the computation up to you, but you end up getting 20 minus 15 over 2 minus 1. And so you get an average rate of change of 5 for this first one. Okay, and I'll change colors here. for the second one, the computation that you have to do is 15.23. That corresponds to a time at 1.1, again minus 15 and 1, and you end up getting 2.3 here. All right, and now the other pattern that you want to keep in mind or to notice is that the time is the delta t, the change in time, is getting smaller each time. Going on, you get 15 point, let's see, 0203 minus 15 all over 1.01 minus 1, and then this comes out to be 2.03. And then the last one, I'm not going to go ahead and write this down, but you end up getting an average rate of average velocity, of 2.003. Okay, so then based on these approximations, you can see you go from 5 to 2.3 to 2.03 to 2.003. So I think it's safe to say that the instantaneous velocity, we have to look at the limit of these as we decrease delta t, and as we decrease delta t, we get closer and closer to just 2. And then adding the units in here, it would be feet per second. Okay, so then the equation of the tangent line, well, if we treat this as our slope, as our s prime at 1, okay, so I'll label this as s prime at 1, our function, and I really shouldn't say s of t, it's kind of a bad notation, I'll just say y, is equal to s of 1, and then times t minus 1, and then whatever the position is at that time. So going ahead and writing that out. So let's see, I just have 2 t minus 1 plus 15. And that'll be the slope of my tangent line. Alright, last problem here. This is the graph of f of x, and we want to sketch the graph of f prime if f prime of 0 is equal to 0. So we have a point, but now I need to graph the f prime. So that is the slope of, or the slopes of the tangent lines. So let's see. I'm just going to pick a few nice points. Let's look at minus 1. That slope, and this is all just an estimate, so that slope to me looks to be a minus 1. So I go down here, and a minus 1 is going to be right here. So the x value doesn't change, but the y value is now the slope at that point. So at 2, that slope is decreasing, and I'm going to estimate that to be a minus 3. So that's going to go right about there. Again here, this is, I don't know, maybe a minus, that looks to be almost a minus 3, maybe a minus 4. So I'll put that there, and then that's enough points on that direction. As I go out to 1, this is positive, and it looks to be about a 1. So I'll just make a point here. That one might be a little confusing to read. At 2, I look at the tangent line. So the tangent line is going to look something like that. The slope of that, I'm going to say it's about 2. Oh, and that other point should actually be down more, come to think of it. So we said the slope here was about 1, so that would be right about there. At 3, I don't know, that looks to be maybe, the slope of that's maybe a 4. And this is all kind of just estimation. So again, it's a sketch, not an exact graph. So if I were to draw draw f prime, all I have to do is connect the dots. Okay, so f prime actually looks to be a line, and for reasons, and this does make sense given that the graph is a parabola. And we will actually see in Module 3 how to determine determine f prime more precisely. Okay, just a few brief examples on Module 2. On Module 2b, we will go through a lot of these problems in class, and it's a lot of computation. Okay, so again, average rate of change, instantaneous velocity, slope of a tangent line, slope of a secant line, all connected.